Hi class, in this video we're going to talk about section 5.5, graphs of other trig functions. And so recall from last time, if we had some general point xy, right, and that connected from the origin 0, 0, we could call this distance between the origin and xy r. And for a general point, which we had in our unit circle, we defined our trig functions. So we said sine, and if this angle here is theta between the x-axis and our ray, right? Remember, we could think of that as a ray. We said that sine of theta was equal to y over r, and we couldn't have this point equal to the origin, so r isn't 0. We had cosine of theta, which was x over r. Again, r not 0 because we can't divide by 0. And tangent of theta was y over x. And so we can't have x equal to 0 in this case. So we can't be on the y-axis. And then our reciprocal functions, right? Remember, cosecant of theta is just 1 over sine of theta, and so that's r over y. Y now can't be 0. Secant of theta is 1 over cosine of theta, which is r over x, x not 0. And cotangent of theta is 1 over tangent of theta, or x over y, y not 0. And so this is how we had defined our 6 trig functions for some arbitrary point P, where theta is the angle between that ray and the x-axis, always measured from the x-axis counterclockwise, and r is the distance, remember, which is just our distance formula, x squared plus y squared, and you take the square root. All right. And so last time we graphed our sine function and our cosine function. And so I'll pull those up real quick just to refresh our memory, where we had sine of x, which looked like this. So sine of x is 0 at 0. It's 1 at pi over 2. Again, 0 at pi. At negative 1 at 3 pi over 2. And then it's back to 0 at 2 pi. And so that one full period from 0 to 2 pi, we go up to 1, back to 0, to negative 1, and over. And then we had our cosine function, which looked like this, which, remember, we had our relationship that sine and cosine are just shifted by pi over 2. So if you shift that whole sine graph to the left by pi over 2, we now start at 0, we start at 1, we go to 0 at pi over 2, we're at negative 1 at pi, 0 at 3 pi over 2, and back at 1 at 2 pi. The period is still 2 pi. And so let's go ahead and graph our tan function, our tangent function. And so I've already saved us the work of pulling all of these values off of our unit circle. And so make sure you have your unit circle somewhere where you can access it. Right, we had each of these points, and tangent is just sine over cosine. So we have a half over root 3 over 2, which reduces to 1 over root 3. And then here we have 1 over root 2 over 1 over root 2, which is just 1. Root 3 over 2 over a half is just root 3. But here, when we have 1 over 0, we're undefined. And so it's important we know the points where it's undefined. So if we look back at our definition, which was on our first page, we said that we couldn't have x equal to 0, and that was here on the y-axis. So we'll have another undefined point up here at negative pi over 2, zeros here at 0, at pi, and negative pi. And you'll notice that here I'm going between negative pi and pi. We could just have easily gone between 0 and 2 pi because we had 0 to 2 pi here, but often I find it's easier to think of this as positive pi, and this is negative pi, and all of our values are unchanged. So let's get to graphing, and I'll use a different color. So let me make sure I don't go too far off the screen. Here at 0, we're at 0. And then at pi over 2, we're undefined. And we know that's because we can't divide by 0. And whenever we're undefined, we end up with our vertical asymptotes. And so let me go ahead and put in all my zeros. So we have one at 0, and we have one at pi, and then we have another vertical asymptote here. And then moving left, we have an undefined at negative pi over 2. We have a 0 at negative pi, negative 3 pi over 2, if I could stay on the vertical line. And then we have a 0 at our plus and minus 2 pi, because that's the same as 0. And then if I plot some of these points, so we'll go march to the right of 0, we're at about a half, and then we're at 1, then we're at 1.7, and if we follow that trend, we're going to end up with something that looks like this, reaching up towards infinity. And then I'll march backwards from 0, negative about a half, then we have negative 1, negative 1.5, and it'll look something like that. And remember, these are vertical asymptotes, so while it might get closer and closer to that asymptote, it'll never quite reach it. And then if we move further left, here at negative pi, we're at 0, about a half, 1, a little over 1.5, we have that, and that, and that. And move over to pi, we're at 0. To the left of it, we're at negative a half, negative 1, a little bit more than that, something like that. Right, and we know that it continues that way, but I don't quite have that marked, and I don't have it that way marked. And so for whenever we're talking about our tangent function, we're going to often look at this as our main period, from negative pi to pi. So remember, it has a period of pi, because this pattern repeats every pi as we march along. And so let's write some of the characteristics of this graph. And if you want to see what that looks like on your calculator, if we go to y, I'll get rid of those. If I graph tangent of x, and then make sure you're on zoom trig, which is, oh, excuse me, zoom 7, which is trig. It's taking its good old time to draw our trig function. I think I broke my calculator. Y equals tangent, zoom, trig. There we go. Now it's drawing a little. I didn't think it should take as long as it was. And that looks pretty close. So here we have y equals tangent of x. And so what are our characteristics that we need to know about our graph of tangent? And so I'll put this here. So we know that its domain is all real numbers except except what? Well, we had vertical asymptotes at pi over 2, 3 pi over 2. We would have one at 5 pi over 2. So those are the odd multiples of pi over 2. So an even multiple of pi over 2 would be 2 pi over 2, or just pi, and it's defined there. The range, we have these asymptotes, but it reaches up towards infinity and down towards infinity, so our range is negative infinity to infinity. Our zeros are at our even multiples of pi over 2, or our integer multiples of pi. The period, right, that's the width it requires for the whole pattern to repeat, is 1 pi. The vertical asymptotes, well, that's all of the points where it's undefined. Those are our odd multiples of pi over 2. odd multiples of pi over 2. And in terms of symmetry, we have symmetry about the origin, because for our first point it goes up about a half, the point to the left it goes down, and then we have up 1, down 1, and we call that odd symmetry or origin symmetry. And so those are important properties of our tangent function. And whenever we're working with transformations, we still apply them in the help students remember variables, horizontal shifts, then stretches, then reflections, then vertical shifts. But let's look at the other three functions. So now let's think about the graph of cosecant. So this is CSC of x, y equals CSC of x. And first let's remember that cosecant of x is just 1 over sine of x. So let me go ahead and get my graph out. And let's graph our sine function. So remember, sine starts at 0, marches up to 1 at pi over 2, back to 0 at pi, negative 1 at 3 pi over 2, back to 0, and then we follow odd symmetry. And our graph looks something like that. So that's y equals sine of x. And if our relationship is cosecant is 1 over sine of x, 1 divided by sine's value. Well, here at 0, sine's value is 0. And 1 divided by 0 is undefined. So we know that we can't have a value here at 0. Here our value is 1, so 1 over 1 is 1, so cosecant has a value there. Pi over 2, pi. 1 over 0 is still undefined. 1 over negative 1 is negative 1. And then 1 over 0 is undefined. And so you can already see what our period is at least going to have some factor of. Something special is happening with the pi. And we also know that we have a positive 1 here and a negative 1 here. So since sine's period was 2 pi, we have that cosecant's period is also 2 pi. So period is 2 pi. We'll just go ahead and write that. And because we can get that from this graph. 1 over 0 is undefined. 1 over negative 1 is negative 1. 1 over 1 is 1. And keep going like this. And if you have your table from last week's videos, go ahead and look at your sine function values. You can do the reciprocal of each of these. All of these are less than 1. And when you take the reciprocal, they're going to get bigger than 1. And when we get close to 0, we're going to get a very large number. And so it turns out that our graph looks something like this. And you guys could construct a table, but at this point we've graphed enough of these by plotting points that I think if I just go ahead and skip to, this is what our graph looks like. You'll be okay with that. So that's y equals cosecant of x. And so we need to write all of our properties. So our domain, I'm going to leave the period there at the top, our domain, well, it's all of our real numbers, except what? Well, when we have 0 pi, 1 pi, 2 pi, so domain is all reals, except our integer multiples of pi, right? And that's because that's where all of our zeros of sine correspond. Our range, well, notice we have a really interesting phenomenon here. So here our range is 1 and up to positive infinity. And down here our range is -1 and down to negative infinity. So our range is anything from negative infinity to -1, including that -1, union or together with 1 and including it up to positive infinity. So our range is disjoint. Cosecant has no value between plus or minus 1. So there is no cosecant value of 0, say. The period we said was 2 pi. What about x-intercepts? Where does this intersect the x-axis? It doesn't. It has none. Is it even or odd? So in terms of symmetry, it's odd, because if to the right we're up at 1, to the left we're at -1, and so we have our symmetry there if we would rotate it about. And our vertical asymptotes, where are those? Well, we have them at our integer multiples of pi. Not too bad. And so if this is what our graph of sine and cosecant look like, what do we know is true about sine and cosine? That they're just shifted pi over 2, right? And so we're going to see that same phenomenon. But before I move on to that, let's go ahead and get our handy-dandy calculator. So here we had sine of x was in blue, so sine of x is in blue. And then we had cosecant, or 1 over sine of x. So we'll graph this. So there's our sine function drawing in, hitting those zeros at our integer multiples of pi, and there is our cosecant function. And that looks pretty dang close to me. Good. So moving on to secant. So this is the graph of secant of x. Well, remember y equals secant x is just 1 over cosine of x. And so we'll follow the same color convention where we have blue. It will be cosine, so y equals cosine of x. And then we'll have y equals secant of x in red. But cosine starts at 1, goes to 0, then -1, back to 0, and then back to +1. And march away the opposite way. -1, 0, 1. So that's y as our cosine of x. And again, remembering that secant is 1 over cosine. So anytime cosine is 0, we'll have a vertical asymptote. One over 1 is 1. 1 over -1 is -1. 1 over 1 is 1. That pattern continues. And what we have here for our secant function is precisely what we expected, which is just our cosecant function, and I'll go ahead and write the rest of those in just so we don't think it stops, is just precisely our cosecant function, which started like, I wish this was on a transparency now, shifted to the left pi over 2, right? Our next one we would expect to be up here. And so our properties of secant, I'll keep this here so we can see it. I'm going to do our domain, our range, our period, our x-intercepts, whether it's even or odd, and our vertical asymptotes. So our domain, well, it's defined for all real numbers except those odd multiples of pi over 2. So it's all reals except odd multiples of pi over 2. Our range, just like we had with cosecant, is from negative infinity up to negative 1, and then we jump up to 1 and go to positive infinity. So we have negative infinity, negative 1, union 1, positive infinity. Our period goes from negative pi over 2, or let's think, there are lots of ways to think about this. Negative pi over 2 to 3 pi over 2, which is a difference of how much? 2 pi. You could also say, well, if I start here at 0, I need to go all the way to 2 pi before it starts to repeat. So our period is still 2 pi. It has no x-intercepts because it never touches the x-axis. Just like cosine was even, secant is even. And vertical asymptotes, again, are at these points where it's not defined. So the odd multiples of pi over 2. All right, and we have one more to get through, but before we do that, we'll go ahead and graph it. So now we have cosine of x, 1 over cosine of x. So we graph our cosine function, and it looks something like that. And then our secant function looks like exactly what we expect. Those kind of parabola-looking shapes that touch our functions at our peaks. All right, one more. The graph of our cotangent function. Graph of cotangent. And I know we just drew tangent not too long ago, right? We had something that looks like this. So let me go ahead and just copy the first one over. We have vertical asymptotes at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. And then I'm just going to go ahead and draw in the first one. So it looks something like that. And if it's okay with you, I'm not going to write any more of the other ones there, right? We know that it repeats over here, over here, over here, and over here. Just like we had here. Now still we have that y equals cotangent of x is just 1 over tangent of x. And so let me put my labels so we can keep track of our graph. Y equals tangent of x. And then blue will be y equals cotangent of x. Now we had at this point over here, so we had a half and then a 1, right? We had a 1 right about here. So we know that that value won't be changed. And the same with negative 1. That one actually fell on the 1 like I wanted it to. But here, at this point, we have 0. So 1 over 0 is undefined, which means our cotangent asymptotes get shifted. Tangent is 0 here. cotangent is 0 here. Sorry, I just hit the camera. Tangent's here, so cotangent is undefined. Tangent is 0, so cotangent is undefined. And so if we move at pi over 2, we have infinity. Now, why did we have an infinity, or an undefined? Because if we looked at our unit circle, here we had tangent was 1 over 0. But cotangent is going to be 0 over 1. Well, that means our cotangent function is 0 here. And then over here, instead of being 0, it's going to be negative 1. Or not all the way over. At this point, we're going to be at negative 1. And so if I'm going to have to trust I'm interpolating a lot of points here. And I'll draw in a couple more so we can see them. So everywhere tangent had an asymptote, cotangent has a 0. Everywhere tangent had an asymptote, cotangent is 0, right? So the reds were tangents, asymptotes, and our cotangents, asymptotes get shifted. So let's graph this one on our calculator. Y equals tangent of x, and then 1 over tangent of x. So there's our tangent function. Oh, my colors don't match. Give me a second. There we go. Now blue is cotangent, which is in fact what it looks like. We have that asymptote at our y-axis, and there's our tangent. And that's kind of a fun looking picture. But notice all of these points where they have in common. This negative 1, because 1 over negative 1 is negative 1. At 1, 1 over 1 is 1. When it was 0 for tangent, we have a vertical asymptote. And where we had a vertical asymptote for tangent, cotangent is 0. So our properties. So let me write those two things because that's important to know. So tangents, vertical asymptotes, correspond to the zeros of cotangent. And the zeros of tangent correspond to the vertical asymptotes of cotangent. But properties of our cotangent function. The period, just like tangent had a period of pi, cotangent also has a period of pi. So the period is pi. So sine, cosine, secant, and cosecant all have a period of 2 pi. Tangent and cotangent both have a period of pi. The domain are all the real numbers except, so where do we have our vertical asymptotes? So we have one at 0, at pi, at 2 pi, and those are integer multiples of pi. Our range is all reals from negative infinity all the way up to positive infinity. We have x-intercepts where, so that's our blue function, pi over 2, 3 pi over 2. Those are odd multiples of pi over 2. Is it even or odd? it is odd. So just like tangent was odd, cotangent is odd. And if cosine was even, secant was even. So the parity, that's a word I want you to know, parity. Parity is just evenness or oddness. But parity is the general even or odd word. So the parity is odd. And our vertical asymptotes are at, again looking at blue, 0, pi, 2 pi, and we said those were the integer multiples of pi. So what is it that I want you to be able to do with these graphs? What you should be able to do. Most importantly, I want you to recognize the graphs of the 6 trig functions. So that's your cosine, so y equals cosine of x, y equals sine of x, y equals tangent of x, and their reciprocals. Cosecant of x, secant of x, cotangent of x. I want you to understand how help students remember variables affect the graph. But that's using a graphing calculator. So unlike when we were talking about sine and our linear functions and our quadratics, where I needed you to be able to piece apart every single change that was happening, if you have, say, sine of x, and then you have, say, sine of x plus pi over 2, and maybe we multiply that by 2, and then we add 4. I'm going to be like, well, sine is our starting function, and then I have a horizontal shift where the whole thing goes left, where there's a scale, and I'm going to have to zoom out because it's off our screen. So there's our sine. And this one was, what was it? 2 sine x plus pi over 2 minus 4. 2 sine x plus pi over 2 plus 4. So know that that means scale 2, shift pi over 2, left, shift up 4. But really just recognize which of those functions it would be. I don't need you to break it down quite in such detail. And then the third thing I want you to be able to do, so recognizing the graphs, understand how these transformations affect the graph, and I want you to be able to tell me where the points on the graphs come from. And what do I mean by where the points on the graphs come from? Well, we know that points on the graph are the solutions to our equations. And so I want you to know that sine of theta, cosine of theta, and tangent of theta are all defined as y over r, x over r, y over x, and cosecant of theta, secant of theta, and cotangent. Oh, I'm off the screen. trying to be more conscious of when I move off the screen. R over y, r over x, and x over y. So that if I give you some general point, I want you to be able to tell me where these trig functions are. And so if I was like, well, tell me the trig value of tangent of pi over 4. Well, I want you to know that that's our y value over our x value at pi over 4. That's 1 over root 2, 1 over root 2, which is just 1. And I want you to be able to tell me, well, that means that this point right here, where it's equal to, oh, I don't, let me cover up those plus and minus 1s. I wasn't using that scale. This here is at 1, because that's pi over 4. And that's what I want you to do. So there was a lot of build up to getting to these graphs. I want you to recognize these graphs of the 6 trig functions. I want you to know their properties, right? And that's what's going to help you recognize them. You're going to recognize them based on where the asymptotes are, what the domains and periods are. So recognize graphs and their properties. Understand how the graphs shift using your graphing calculator, and how those graphs relate to these coordinates on our unit circle. And if you can do that, and that's kind of bringing together the last 2 or 3 lessons, I think you're golden on our trig functions so far. Have a great day, everyone. I'll see you in the next video.